In the last class, we have discussed about the shear stress in beams, and we have derived the expression for the shear stress for a beam. And if we look at the equation that we have derived in the previous session, it was tau is equal to F A y bar divided by I into B, and we have explained all the terminologies in the equation. Now we will move forward and see what is the distribution of shear stress. What is the nature of distribution in shear stress in a rectangular cross section? So what we will do is, before moving into this distribution part, let us derive the actual equation. So we have the depth as d, and if we take half the portion, this is going to be d by 2. And I told that we are going to discuss about this particular fiber. So whatever might be the fiber you consider, you have to consider the area which is lying above the fiber. So the shaded portion shows the area that we have to consider. So this is the centroid of that particular area, and the y is nothing but the distance from the neutral axis to that particular centroid. So how can we write the value of y bar? Equation is tau is equal to F A y bar divided by I into B. Okay, so we know the value of I is nothing but B d cube by 12. That is for the entire cross section, we cannot change that. And B is B itself. F is the shear force that is available from the shear force diagram. Now we are bothered about the A and y bar. So let us first define the value of y bar. So y bar is equal to y plus d by 2 minus y. So d by 2 minus is this distance. D by 2 minus y is this distance, and half of this value is going to be added to y to get the value of y bar. So from here to here it is y, and half the portion is d by 2 minus y divided by 2. So altogether it is going to come as y plus d by 4 minus y by 2, and we can rewrite this as y by 2 plus d by 4. If we take 2 common outside, it can be y plus d by 2. This is the value of y bar. Now we need the value of area A, which is equal to breadth into thickness, and B into what is the value of this side? It is d by 2 minus y. So this is going to be B into d by 2 minus y. Now we will substitute the entire equation, this first equation and the second equation in A. So 1 and 2 in A gives what? Tau is equal to F into B into d by 2 minus y into 1 by 2 into y plus d by 2 divided by I is B d cube by 12 into B. So this B and this B will get cancelled out, and what is left with is tau is equal to 1 by 2 into F into, if we look here, we can say that this is of the form A minus B and this is A plus B. So if we multiply A minus B to A plus B, it is going to be A square minus B square. So the answer is going to come as d square by 4 minus y square. This half we have taken out here and divided by B d cube divided by 12. Okay, so or in simple words, we can rewrite this equation as F divided by 2I into d square by 4 minus y square. So if we look at this equation, we can say that the distribution of shear stress is a parabolic in shape, because we have an equation with y square which indicates the variation is parabolic, and that is being shown here. Now why it is 0 here, why it is maximum here, and again 0 here. See, we have already discussed that the shear value increase as the value of A y bar increases. So you have the maximum area and y bar just above the neutral axis. So in a way we can say that if you when we consider a fiber, I told you that when you apply a bending moment on the beam, a cross shear develops and is acting in the longitudinal direction of the beam, not in the transverse direction. So the effect can be seen in the longitudinal direction. So if we go deeper and deeper into the beam from the surface, more and more force is required to make the beam undergo deformation in that particular. For example, if you take a beam like this, the amount of force required at this particular fiber is less when we compare the force required to deform this particular fiber. That means the force in the sense means the shear force. Because if we consider the first fiber here, the amount of restraining area or the resistance offered by the area which lies above the fiber is less when we compare the neutral fiber or any fiber. So when we consider the neutral fiber, more amount of area is being added on the top, which offers additional restriction, thereby limits the deformation. So that is the reason why we have a maximum value of shear stress in the neutral axis. So that can be concluded in such a way that we can expect to have a maximum value of shear stress at the neutral axis, and towards the two sides it is going to reduce and finally reaches to value of 0. So at the ends we have the value 0, and at the neutral axis we have the maximum value. So this is how the distribution of the shear stress in a rectangular cross section look like. Now what will happen if we let us see what is the distribution at y is equal to d by 2. Let us solve it like this. At y is equal to d by 2, what happens? Tau is equal to 0, because d by 2 the whole square is going to be d square by 4. These two will get cancelled out and we'll get the value of 0. So tau will be equal to 0. What will happen at y is equal to 0? Y is equal to 0 means at neutral axis. Here y is equal to 0 and here y is equal to d by 2. This condition. So if that is the case, what is the value that is going to come? Tau is equal to f divided by 2 into y, d square by 4 minus d square by 4, y is 0. So f into d square by 4 divided by 2 into b dq by 2 into b dq by 12. So upon cancelling the similar terms, this 2 will get cancelled out, and what we are going to get is 3 by 2 into f divided by b into 2. So this b into d is nothing but the area. So what can be written as tau max is going to occur at y is equal to 0. At y is equal to 0, what we are going to get is 3 by 2 into f divided by b into d, or in other words we can say that it is 1.5 into f divided by area, and this area or this f by a can be called as the tau average value. So in short we can say that f max is equal to 1.5 times the average value. This is a very important relation which can be used with the rectangular cross section, where the maximum value is the 50% higher than the average value. Average value means you take the maximum shear force and the total area. It is going to be the average value, and the maximum value is going to be 1.5 times the average value. So this is how the distribution of a shear stress in a rectangular cross section will look like. So kindly go through this derivation, and next session we will discuss about the shear stress distribution in I section as well as the T section.